Hi everyone, today we are going to review the paper BiACT, Bilateral Control-Based Imitation Learning, authored by Masato Kobayashi and colleagues from Osaka University, Japan. This paper builds upon the concept of action chunking transformers or ACT. So let's get started. Imitation learning algorithms typically learn from expert demonstrations. But even with high quality data, acquiring certain skills can be challenging if the model is suboptimal. Traditionally, RNNs and LSTMs have been used to handle time series data in these models. Recently, we have seen transformers employed in papers like ACT to handle time series data, successfully mitigating issues like compounding errors that arise from minor inaccuracies in predicted actions. ACT predicts actions by utilizing joint positions and image information, but it does not incorporate force information. An imitation learning algorithm proposed by Skyno uses both position and force information, but it relies on LSTM for handling time series data. Enter BiACT. This new approach is trained using joint angles, joint velocities, and torque along with the image information. The robot operates via bilateral control, leveraging both position and force information. This allows to adapt to the hardness and the weight of the object, a feat that was not possible with just position control. As multimodal data handling robotic system, BiACT utilizes action chunk, achieving a frequency of over 100 Hz. This enables fast and robust motion generation in an imitation learning system that incorporates image data. The controller in BiACT is designed to use position and force information on each axis. Angle information is obtained from the encoders, while angular velocity is calculated using differentiation. Disturbances such as external forces, frictions, and changes in the load can affect the desired operation of the system. To counteract this, a disturbance observer is used to estimate the disturbances affecting the system by observing the differences between the expected and the actual behavior. This estimation is then used to adjust the control inputs, compensating for the disturbances and ensuring the system continues to follow the desired trajectory. The reaction force observer observes the motor currents, positions to estimate the external forces acting on the joints. It utilizes the known dynamics of the manipulator such as mass, inertia, and friction, along with the control inputs to infer the reaction forces experienced by the manipulator during operation. The fundamental principle of bilateral control is the sharing of position, force, and other information between operator and the control target. This is achieved using these equations that ensure that the follower matches the joint angles of the leader and enforces reaction torque on the leader arm. This process allows human operators to feel the reaction forces from the follower during data collection, thereby enriching the data collection process and improving the data quality. In the control block diagram, we see that the leader controls the follower robot using the position and the force information with the help of the position controller and the force controller. During inference, this leader robot is replaced using a neural network model. The follower robot is controlled by receiving the predictions of the leader's response. The learning architecture is similar to ACT, with some changes in the input and the output dimensions. The model processes the joint angle, angular velocity, torque for each of the 5 joints. Action chunking is utilized similarly to predict the leader's actions over the future time steps. The leader's actions for these time steps are then conveyed to the controller, which determines the current required for the joints in the follower robot, enabling it to move in the specified direction. The experiments conducted in the paper involve an environment with two 5DOF robots in the leader-follower configuration, equipped with wrist cameras and overhead cameras. The tasks involve picking and placing different objects, opening and closing drawers, and placing objects inside them. The objects vary in shape, size, and texture, demonstrating the model's capabilities in handling deformable objects and previously unseen items. Notably, one experiment showed the model's ability to manage objects containing liquids, which is particularly challenging due to the shifting weight as the liquid moves. Check out these results from the experiments, and for more details, be sure to give the paper a read. For more exciting paper reviews, make sure to subscribe to our channel. And I'll see you in the next video. Thank you.